Welcome back, guys. So last week we were just mostly working on passing the first block, which is the zeroth block, and trying to get the supernode and its metadata. We did manage to finish a little bit of things around it. We managed to pass a lot of metadata from that super block, and we have wrote down what to do next, which is to read the second block, and the second block, which is index 1, and we get the gdt from it, and we can read whatever gdt provides, and then we have the inodes parsing, and finally we have the data blocks, actual data blocks parsing. So yeah, so today this week, let's focus on finishing at least till inode parsing, and maybe have some example of reading a full file, something like that. So overall, we're still finishing up our own kernel. We have the memory management unit. We have scheduler. We have virtual space. We have interrupts. We have syscalls, and we also have the block layer. Now we are currently working on the virtual file system layer, and currently we're going to only support one front end, which is the X4 front end. And last week we learned a lot of interesting things like the sparse file setup for the X4. So yeah, let's dive into the actual implementation of parsing block 1 this week. Oh, okay. Okay, so we want to read block 1. Okay, maybe we can write a helper. I think we can move this entire thing into some helper like super block parsing, because right now this function is already too big. Okay, it's fine. Let's just write that here then, and it's a function that's just going to pass the block 1, and it's going to read some certain things. So let's just say parse ddt. It's ddt, right? Global description table, gdt. Yeah, it's gdt, it's not ddt. ddt global descriptor table block, and it's gonna take maybe it needs to take certain values that we parsed from the previous block, because in the previous block we did manage to parse the number of groups, number of inodes, descriptor size, also block count. I think this, maybe we can pass these informations down to the next function. But do we need it? I don't know. Let's just put one unit 32-bit star args. So we're just getting a uint 32 point array, so we can pass as many as we want, and we can just use the index here. And okay, first we need to understand what do we want to do here. To do all the thing that we can parse in this block. This is what we need to understand first of all. So if we go back to, I think it's in second, yeah. Okay, so yeah, Last week we were going through this part, which is the super block fields, and we managed to parse each field based on the offsets. This week we do have an intermediate step after passing the super block, which is to hi, which is to set up the features that are actually compatible, because we can read the feature flags and see if the file system actually supports those stuff. But we are not doing that. Yes. And what architecture are you writing it? Which architecture? Maybe it isn't here. Okay. Yeah, writing. I'm not actually writing in OS. I'm just writing kernel. Okay, jumping into kernel. So you're still in your bootloader. Okay, you're using x86. Fine. Okay, did you start? You are still in your start. So you jumped from the was it initial instruction from reset to start, or are you using Chemo? Because if you use Chemo, you don't have to jump anywhere. You are already inside the start. Good. Okay. Fine. Okay, where did I leave? Yeah, here the feature flags. Every file system actually has a lot of feature flags, and we can read it, and we can get an understanding of what sort of features that are actually present, and do we even want to try to parse, because in X4, if the feature flag says that sparse files are supported, then we might have to see the blocks of zeros or empty blocks as zeros. And if the feature flag is not supported, then we can just throw an error. So yeah, that sort of stuff. Okay, if you're using Chemo, then probably you are inside start and you are trying to jump into kernel. Okay, how do I do it? It's my fucking starts. Yeah, it's here. Yeah, my start is really simple. I just disable interrupts, put the stack and 0 BS, set the vector table, and enable MMU. This is a big part, but I enable MMU, and then I think you should be able to do it on your own. I don't think you'll need this. And then what do I do? Varpel. Yeah, this is the what's it? Vector table after I enable MMU. Yes, before I enable MMU, the vector table is in a different address, and after I enable it, I'm just making the FFFs and bring it there, and then I guess I'm jumping into the virtual entry. I mean my virtual system, virtual range, and then I jump to my k-main. That's it. Yep. Yeah, you should be able to do it on your own. I think my streams are just for fun. Okay. Did we leave? Yeah, we have the feature flags. If we parse them, we can get a better understanding of what sort of features we actually have to read instead of assuming anything that it might exist, it may not exist. That's my file. Okay, it's here. Okay, and then we have the GDT parsing. So this is the initial group table. So as we know, the file system in general is going to be just a bunch of groups, and every group has bunch of blocks. So we need to know as a physical, the entire physical block is divided into multiple groups, and every group is further divided into multiple blocks. So when we read the 0th block, we get to know how many groups are there and how many blocks are there per group. This is what we parsed, and now we do have that information. So we have the number of groups, number of blocks. We also have inodes per group, and we do have something called descriptor size, which I have no idea what means. I guess I fucking forgot everything. So it's GDT block. So by reading block 0, we were able to get these metadata, and then by reading the first block, we should be able to actually get the understanding of the actual groups on its own. So like every group will have what is it, inode table and tables like that, and then it will have the actual data blocks. And we also have certain groups that are considered as backup groups. So in those groups, the first two blocks will have the super blocks backup, something like that. So this table will allow us to understand this entire structure. Okay, so let's see what's inside the table. Each entry is descriptor size bytes. Okay, so every entry within this table is going to be of size, descriptor size, so which we already read. So I guess we need to pass that as the first argument. So let's just create a uint 6032 args, and let's assume that we are only gonna send 5 arguments and args of, we have I int I equals to 0 and I plus plus, and the first argument which is going to take it as descriptor size. So far we only have one argument, and then we can call parse GDT block with this args, and it should be good. Yes, if we want more arguments, we can just add them here, and the parse GDT will get those arguments. I'm using array here because it will be too cumbersome to put every argument here, and probably if we want to pass everything here, then there will be 5 arguments, and having 5 arguments for a function is not good. I mean, not for any performance reasons, just for readability, it's just not good. Okay, so first we know that every entry within this table is supposed to be of size, disk size. Okay, and then for 32 groups, we also need the number of groups, because that will be the total size of this table, because every entry is going to be a group, right? So number of groups Oh, fuck me. I fucking forgot what I even just said right now. And it's going to be number of groups. Okay, the second entry is the number of groups. So we know the table size now. We also know the table per entries total bytes. Okay. So we can actually do this math to actually go into any index. All we have to do is just take the base address plus which index. If we want to access, let's say, third index, base address plus third index into the size should give us the thing. So yeah, let's do that. We can put it as static inline. Put static inline. And what the fuck will it return? So it's going to return size of bytes. Okay. So should we consider it as uint 8 bytes or char bytes? I think let's just use it when it comes without having to create random functions. We'll have the first value, which is block size. No, descriptor size. And it will be args of 0. And we have even 32 descriptor size, and then we have number of groups, which is args of 1. If we have this information, all we have to do is just what do we do now? Now we can read the actual bytes first of all. So let's see, char star puff, and we need schemalog, and we need 4096, which is the block size of the block, and we can read it, and it should be uint 64 red equal to block read, and we need to give the sector we want to read. We want to read the first sector into this buffer and of size 4096, and we are good to go. We can just confirm that read is, if read is not equal to 1, that means something fucked up. You are printf parse gdt schemalog for block read failed, and let's just put what was the code that we got, and we can return here. Okay, what now? Now we have the block, we know the descriptor size. Yeah, now we can just do the math, which is, let's say we want to fields within one descriptor. So every So every index within this table represents a group in the physical block. So that means, so every entry will have all those fields. So if let's say yes, these all those fields will apply for every entry. So every entry will have all those fields. I think so, yeah. And nothing much is there. Let's just say that let's just say I know what I mean. Like I'm able to. I should be able to read now. I'm just wondering what do I read, and what's the point of reading it. So if I read the block bitmap, what information can I actually get? I'll get the location of the bitmap block bitmap table for this group. Okay. And it is just going to give the physical block of groups bitmap. That particular groups bitmap table is located in this particular block. Okay. And the entire table will be of block size, so we don't have to worry about the size. The entire block is the table. Okay. And we can also read this similar way. We can also read the inode table. And we do have free blocks count, and we have free inode count. We also have directory count. Okay. We have checksum. And that is all. So let's just start reading it. Do we have to read for every block? That depends, right? So in case, let's say my file, let's say I want to read etc password, and that is in, let's say, group 5, then whenever I call etc password, read etc password, the first thing I have to do is I have to go to this descriptor table and figure out which block this fucking thing is present. But how? As soon as I get the function, maybe a read operation is after open operation, so the actual open operation would have went through what? No, I don't remember how the entire flow will be able to read a function. Now, what I'm trying to understand here is that, let's say from user space, I just call open slash etc password. What happens now? The moment I get into, I think I wrote it down somewhere here. Okay, user space will pass one FD as FD number. Okay, yeah, and we get into the process. We take the file table and we get the respective file structure. Okay. Okay, so every file will also have its inode. So we know the inode number. So as soon as we know the inode number, we can just use the inode number is just indexed within the inode table. So let's say we have inode something inode index as 5. Then how will we find the group? Understand how we can use the inode tables and the index that we stored in the file structure to go to the inode table and get the logical block and then convert it into physical block. So okay, I understand this flow. Only part missing, or at least from my fucking mind, is that how are we gonna find from which group's inode table we want to use, because every group has its own inode table. Okay, it's time to ask the question. If I have a inode for file, I can index the inode within the inode table to get the extents, which in turn would give me the logical blocks. But I am requesting, like, what happens like how will we know which groups inode we have to use to find the proper, or to find which group the inode belongs to. Maybe it's some sort of calculation. I remember going through the entire flow and it did make sense, but right now it's out of my mind. which block group contains a specific inode. You need to use the inode number and the file system's inode group setting. Yes, so we have inode number. Oh, okay. So inode number will actually be keep on incrementing. Then I can use the inode number -1 divided by group. So I'll know. Okay. Yeah, this is the whole thing. Inode numbers must be globally unique. If it's per group, then we will never be able to know which group it belongs to. Inode number is continuous across all blocks, all groups. Okay, makes sense. Let's fill in that here. User space will pass the, because this is the flow that we need to finish. So user space will pass the FD number not as a file struct inside the kernel. We use the number to get the file struct. Okay, and let's start by saying our process only has 12 maximums. Okay, once we have the respective file structure, we know the current position within the file and how many bytes we want to read from that position. We use inode table to get the data. How did I jump from this step directly to this step? Fuck. The file struct should also have an inode, right? Let's see. Where's my fucking file struct? Yes, it does have an inode. So it makes sense. And the next step is that within the file struct, we have the inode number, which is a unique number across all groups in the physical block. Now we do the math. We use that number divided by number of groups to find which group this inode belongs to. And then once we have that information, now we can use the now we know which group it belongs to, and we have the initial GDT. Now we need to know the inode table location within the group. For that we can read the global GDT and get the particular groups. Inode table location. Then we use the inode table to get the, okay, so these are the steps that were missing. After that it makes sense. Then we use the inode table to get the block that was used by this node. And then we go do the physical mapping, because extends will actually store the logical blocks, and then we can use that. It will have the extends logical block starting number and total, and physical block starting number. That way we can use it to map. Okay. What else? So we have to parse every GDT and keep it in memory, so that we don't have to every time, we don't have to worry about getting the tables, getting the getting the location of inode table within a group. Because within a group there is a block, that block contains the inode table. So whenever we have a new inode, we first get the groups, and then after that we go back to our GDT and get the location of the inode table within that group, and then we go to that location, and within that inode table we get the we do the math to get the logical. No, after that what do we do? I think within the inode table we will have actual extents. Okay, first let's implement this without getting distracted. Now we need to store a global, or can we like every time if we store these information for every block, for every group, then all we have to do is that we do check it in memory. But if we leave it out to reading it from blocks, every time we try to open a file we'll have to go through that parsing, and we have 32 groups and it's going to be fucking hard. So yeah, I think it's better that we implement this and store it in memory. So what we have to do is now we write a for loop, and it's going to be uint32 I, and I less than number of groups, and I plus plus. Now for every index we have to calculate the address. So the address is going to be this logic. Base, it will be like, let's take it as uint64 base equal to, and we take the base address of the buffer plus we need which index, the current index is I, into size of the descriptor. Size of the descriptor is descriptor size. This is the math. Now we have the base address that is just, we'll have 32 base addresses because we have 32 index. So let's say we have, so number of entries within the GDT. Every entry will have specific offsets, like it will have block bitmap location block inode stable location block bitmap table. What the fuck? Inodes bitmap table, etc. Okay, so we have the base, and first of all we need to read we need to read block bitmap. So it's a block event what do I name it? This is going to be event 32 and it's block bitmap lower half, and we can read with the other helpers. It is cast as event 32. Cast as event 32 because this entry is a event 32 value, so we want that. So it's going to be base address plus 0xff 0x00, which is the 0th offset. I'm just explicitly mentioning it so that we know that it's the 0th offset. Reading 0th 0 index. Okay, makes sense. Now we have the bitmap lower half, and we also probably need bitmap higher half, no, upper half, and which is in index 20. Not index, it's better we say offset, because index will have probably for some size. Offset is just bytes. We have a block. Now we can also do the same for inodes. Inode. Okay, now we know inode starts at 04 and the upper half was 24. And now we have, we also have to convert it into one single use event 64, which is block bitmap, and we can use our helper, which is group as event 64, which is going to take upper and lower, which will be block upper and block lower. Perfection. We copy it, we paste it here, and we can change it to inodes. And we can change it here. And it's going to be inode bitmap. Okay, now we have block bitmap and inode bitmap for nth index. we need to store these information for every table. Okay, no, every index within this table. So that's probably 32 index. That's the number of groups. So where do I store this information? Do I have any structure for GDT? Looks like I don't. I have X4 group. No, I do have it. See, I have the block bitmap, inode bitmap. What the fuck is block table then? Ah, okay, this is to say that a particular block is used. And this is to say what? Oh, I fucking forgot. We need to. This is the metadata. This is to store, say, block used or not. This is say inode used or not. Okay. What the fuck is a block table and inode table? I knew this information last week, but it's been a week and I fucking forget every fucking deal. And I don't fucking remember what the fuck this means. What the fuck is a block table? In our flow, it does not seem to have any value. Let's go back to our flow. Let's see if we can infer what that table has to do based on our example flow. What purpose would it serve to hold an inode table on a block table? Because we have the block bitmap, which is going to say whether or not a particular block is used. And what does this table do? And based on our it definitely had something. I just don't fucking was not able to fucking recall it. I guess we have to go back and read it again. Okay, I think we can. I'm not sure exactly. So I'm trying to go back and see. I don't want to assume anything. There's no fucking explanation here. As soon as we finish that, we are jumping into inodes. Okay, it's time to ask questions. Okay, understood what bitmap and block bitmap serves in this table. What does the block table and block inode table values holds? Let's see if it's able to first of all infer my question, or is it considering something else. I need to confirm that first of all. Okay, we have the block bitmap, which is going to be the block number of the block bitmap. And we have the inode bitmap, which is going to be the block number of the inode bitmap. So far good, because that is what we already know, because we have to. Okay, so it's not address, it's just the block number. So then it's just UN32 then. Then why the fuck did I group it as UN64? Whatever. Let's put 64 first of all. If something comes up, we can come back to it later. We have block bitmap, inode bitmap, inode table. That's it. We don't have block table. Why did I assume that I have block table? Oh, fuck me. So now it makes sense. So the inode table is just going to have the metadata about the files. So probably it will have the permissions and stuff like that. So we first, as this explains, the flow starts like this. Once the bitmap tells you that some inode is free or used, let's say we know a file and that has this inode, and we go to the inode bitmap and it says that the inode is indeed used, and then we go to the table inode table location to read this particular index. Right, and you go to this table location. I don't fucking understand. Okay, once I go to the table location, how will I read this specific inodes metadata? Will it be the same index within the table? multiply the index by inode size. Okay, here we use inode size. So we mm, no, I don't understand. Something is missing in my flow. Until this point everything is fine. So now we need to know the inode table location within the group. So we need to read from GDT a particular group's inode table location. First, before this step, we need to check if that inode is already used up in this table. Yep. Only after that I can actually say so here once I have the inode location within the group, I need to go to the GDT table, check if the node is already assigned, and node numbers are always let's see how exactly it will. So let's assume we have a file system with a block size of 4 KB, and we know we have this many inodes per group, and we have inode size of this, and we want to read inode number 25. So first of all, we do the identify the group, that is the inode minus 1 divided by the total number of groups, which would give which group we want to go, which is in this case will be 0th group. And then we read the group descriptor. So we go back to GDT, which is in block 1, and in that we have two fields. One field is the in this table we have multiple entries, and we want the entry of 0th block. So we get the 0th block, 0th index. Within that index we need two fields, which is the inode bitmap field and inode table field, and both are just going to be block numbers. Okay, and then we need to check if the inode is in use. So we go to calculate bitmap position. So bit index is simply 25 minus 1, which is 24. So bitmap. Okay, so the index is actually just the global number, global inode number. Now we exact location within the table. Here also we do the same thing. We use the inode number minus 1, percentage the number of things, and then we get the index. So inode number is unique for all groups. So in case of 0th group, the index is 0 to n, but for other groups the index will start from n to n plus m. Okay, so local index range would still be the same. Only our actual calculation. No, even our calculation does not change, because we know that all our how is the local index 0, then do a full translation example for, let's say, group 5. So we know that this is belonging to 5th group, and then we go what the fuck? Okay, it's a reminder. Okay. Only here we actually do the division. Here we only take the reminder. So because we always use this as the base, a reminder will be the index. Okay, fuck me. I was thinking like, how can we divide a number and get that? Okay, now it makes sense. Now it makes sense. So it's still just calculations that I have to add here, so that next time I don't have to go through this entire process. First of all, number divided by that group would give the which group it belongs to, and then we need to know the inode table location within that group. So we go to the GDT and we get the particular inode table location, which is a block number. Now we have the actual inode table. Now we need to index within the table, so we use inode number -1 percentage number of inodes. This will give the index within the table. We can confirm, we can get the metadata of the inodes. Okay, I mean it's only going to give me inodes, right? Index plus inode size. Okay, this is actually giving us the values. Okay, what happens after that? First of all, we get the inode metadata. No, we got the inode data. Okay, let's say we got the inode metadata. Now what? So if it is a regular file, and then we can actually try to read the yeah, once this is just this is the actual block that will contain the next header. Okay, we use inodes entry to get the inodes extent block. And then we can parse that extend block to actually find the physical address. Okay. Makes sense. Okay, now our picture is little better. Well, once we start implementing it, we might have other questions which we can answer. It should be fine. We have bitmap, and we have both the values, and then we need the inode table. Let's see if it works. Oh shit. I fucking hate. We just copy pasted it, right? What the fuck is this? Let's just why the fuck? Okay. Inodes table upper and lower, base plus inode table is 8, probably 28 in the end. Just double check. Yeah, inode table high is inode block is 20, inode bitmap is 24, inode table is 28. And then we have inode table, which is inode table. It's a 28 and it's 4 and it's 8. Okay. Now we also have the inode table. What else? Once we have the inode table information, now we can just store it for every. Okay, now I remember why I assumed there will be a block table, because this fucking structure has a block table. That's why I was like, what the fuck is a block table? Maybe that's in the super block. Let's see if it's there. I have to fucking remove the history limit. I don't remember where the history limit. It's fucking with me. I fucking hate it. I think it's F1 free practice 3 now. I fucking forgot that. I'm just remembering random things. Whatever. Let's see if we have any super block information. Okay, we have the super block here. No, we don't have any block table. Oh, yeah, why the fuck did I even define that? I don't know. I don't remember. It happened last week or probably the week before that. So I have no fucking clue. I have no fucking clue. And we have the block descriptor. And this one has block bitmap and bitmap table. Yes, that is all. And then we have the inode table. There's no such thing as block table. Why the fuck did I write it? Yes. There's no such thing. Yes. There's no such thing as block table. I saw it somewhere. If not, I would not have added it here. See, we have the super block. We have the group descriptors. And then we have reserved blocks. And I think this is what I mean by that. Reserved GDT blocks. Because this is group descriptor. It's the bigger table that is probably only in the first group. And this fucking thing. Is there any block table in X4? Yep, there's no fucking thing. I must have fucking drunk. Well, let's just fucking paste this and see why it is saying that. Okay, this is only to allow the group descriptor to grow if the file system is resized without moving data blocks. And then we have the data block map, and we actually have the data blocks. There's no fucking block table. Oh fucking hell. I don't know, I probably have to revisit why I even added that. Okay, now we have the bitmap, and this, and also this. This will give the this will hold metadata plus pointer to the extents, which then will have the blocks. Okay. I think we are ready to fill up this. I think we need to put this for loop in the main thing, not here, and it should only get descriptor size. Yes. Yep. That way it will be easy to manage. So we have even descriptor size. I can remove these two. We don't care about, and yeah, also let's take even to current index. And yes, and it's going to return three things, and it's going to return event 32 star outputs results. And we don't have a for loop. We're just going to do it for one index. That will be the current index. You can do this, and we can bring it back. What else? Yes, and we can return the three values, which should be int I 0 result of I plus plus equal to block bitmap, and then we have inode bitmap that is it. We called return. Nothing much. Okay. Maybe we can return bool. And we can return false here. And return true here. Okay. Perfect. And inside mount, we can, now we no longer have to pass anything. We only have to get something. So we need 3. And it's going to be event 64. So we pass descriptor, descriptor size, and current index, there will be I, and it will be results. And it's going to be results. Okay. And it's going to be for event 32 I other than number of groups I plus plus, and we can put this here. Oh shit. And I put this. And I put this. That's it. If it is true, then I can actually prepare the extents. So it is going to be kmalloc, and it's going to be ext for group, right? First of all, I cannot directly create. Yeah, I have to first create group. So it is going to be an X group equal to it's a X for group, and then what do I do? I need kmalloc. But kmalloc size of X for group. Okay, once we have the group, what do? We go group dot block bitmap equal to result of 0, and then we have inode bitmap, and we have inode table. And it's going to be 2 and 1. Okay. Now we also have to finish up the super block. So it's better we super block is same for everyone, right? Yeah, so I can just create one super block and put a pointer to everyone. Yeah, I can create a super block here. So it's going to be super block equal to super block star, and it's going to be kmalloc size of super block, and super block, what do we have? We have block count. I think we have block count, and we have super block inode count, and it's going to be inodes per group. Maybe we'll improve the wording so it will be better. Inodes per group, and we have event 6032 descriptor size, and we have event 32. What else did we actually parse? We go back to our initial fuckity. I think this is what we parsed. Well, let's just take, yeah. We have inodes per group, and we have inode size, inode size, number of groups, it will be number of groups. What else can I actually store in a super block? I have a number of groups, inodes per group, inode size, block count. You can also put blocks per group. Super block, blocks per group, and it's going to be blocks per group. Okay, what else can I put inside that? I can put a block size. Currently we are hard coding block size everywhere. I think that is all. We need blocks per group, inode size, number of groups. Blocks per group and title inode size. Number of groups. Okay, that's all. In that case, our super block is ready, and then we can add that to every group, because every group's super block is the same thing, and super block is of okay. I can just put super block. Every group has a pointer to the super block for some reason in our case. Actually, every group does not have to have a super block, but in our case it does. But it's fine because we are not allocating it 100 times. We allocate once and we just put a pointer here. Now we have the group parsed. Now we have pointers to those groups. We need to store it somewhere. We need to store it in global GDT. So that we can read anytime we want this value. Yeah, let's just let's just create a new thing, that is the type def ext4 struct ext4, and it's only gonna have one thing, which is ext4 groups. Do we need anything else? Groups on their own will have all the other information. Yes, that should be fine. Yes. Maybe we can pre-allocate it as 32 groups. And let's say do we want to do that? No, we don't know. It's going to be x2. Okay. And now I can just return ext4 instead of, it's going to return ext4 pointer. And I'm going to allocate an ext4 here, ext4 pointer ext4 equal to ext4 pointer kmalloc size of x4. Now what do we do? No, size is x4 into number of groups. And what's our number of groups actually? Let's go run it. And we only have 62 groups. And we only have 16 groups currently, so it is fine. It will be within our range. So we have 16 groups. And once we are done, we just add it as no. What the fuck am I even saying? This is just x4. Within that, I have to allocate that x4 and groups equal to, now I allocate something which is kmalloc, and I say size of x4 group into number of groups. In that case, I don't really have to allocate it again here. X4 group would just be x4 groups, and this is my base. What will it return? It will return a case u64, right? And it says x4 group pointer. Groups plus I. I also, I need to convert it into u64. Okay, now I have the base address of the groups, and we have already pre-allocated the number of groups here, so we can just use that groups plus the index to go to that particular groups, and then we make it as an x4 group and we update the values. That's it. We have parsed the entire GDT and create the x4, and we return an x4 here. Yeah, I think that is it. Now all we need to write is parsing inode blocks and next blocks. Now that we have parsed the GDT, we can pass the inode table and then the x extends. Perfect. So what we have done today is that we just managed to write an extra helper which is going to parse the GDT block, and it's going to collect the bitmap address, inode bitmap, block bitmap, and it will also go give us the inode table, and we are put those all into one structure which is the ext4 group, and we also pre-allocate number of x groups, and we create a new structure which is called the ext4, which will have multiple groups, and we also have the super block which will be common among all those groups. And yes, that is all. That is all. Yeah, tomorrow we can just continue with the inode parsing, and once inode parsing is done, we should be able to at least read something from the file system. Okay. Thank you guys. I'll see you tomorrow. Bye bye. Where's my fucking... Okay.